B.A Geography, Geographic Information System. Lesson 9, Geometric Transformation. In the previous chapter, we have learned about different data input and capture method, that is keyboard entry, digitizing and scanning or automated. Along with this, we also discussed about data reduction and generalization, edge matching and rubber sheeting. In this chapter, we will get to discuss about how the data has been converted from one digitized data to other digitized data called geometric transformation. Objectives. In this chapter, we will discuss about the geometric transformation, transformation methods, root mean square error, interpretation of root mean square error on digitized map, sampling of pixel values. Geometric transformation. A newly digitized map has the same measurement unit as the source map used in digitizing or scanning. If the map is manually digitized, then the map is measured in inches as same as the digitizing table. If the map is converted from the scanned image, then the map is measured in dots per inch. Similarly, a newly digitized map cannot be aligned spatially with GIS layer that are based on projected coordinate system. To make it compatible and usable, we must convert the digitized map into a projected coordinate system, whether it is a UTM or a state plane coordinate system. This conversion is called geometric transformation, which in this case transforms map feature coordinates from digitizer unit or dots per inch into projected coordinates. Geometric transformation allows the digitized map to align with the other layers of data display or analysis in GIS. Geometric transformation can also be applied to remotely sensed data and satellite images. Remotely sensed data are recorded in rows and columns. A geometric transformation can convert rows in columns into projected coordinates. Additional to the transformation, this feature can also correct the errors occurred in remotely sensed data, which are caused due to relative motion of the satellite, that is scanners, and the earth, an uncontrollable variation in the position and altitude of the remotely sensed platform. Though some errors can be rectified manually, they are typically removed by geometric transformation. Projection converts data set from 3D geography coordinates to 2D projected coordinates, whereas the geometric transformation converts the data from digitizer units to rows and columns to the projected coordinates. Types of geometric transformation. There are two types of geometric transformation. One, map to map transformation. Two, image to map transformation. Map to map transformation is the transformation done from manually digitized or traced from a scanned file to a digitized map. This is based on the digitizer unit. The unit of digitizer can be in inches or dot per inch. Image to map transformation is generally used in remotely sensed data. Window transformation, rows and columns of a satellite image are transformed into projected coordinates. Another term for the image to map transformation is georeferencing. A georeferenced image can register spatially with other features or raster layers in GIS database as long as the coordinate system is the same. In the geometric transformation, set of control points are used to establish a mathematical model that relates the map coordinates of one system to another or image coordinates to map coordinates. This process is somewhat uncertain due to the use of control points. In the case of image to map transformation, the control points are selected directly from the original image. This makes it uncertain, and misplacement of the control points can make the transformation result unsuitable. The root mean square error is an quantitative measure that can determine the quality of a geometric transformation. It has measures the displacement between the actual and estimated location of the control points. If the root mean square error is acceptable, then a mathematical model derived from the control points can be used for transforming the entire map or image. A map-to-map transformation automatically creates a new map that is ready to use. An image-to-map transformation, on the other hand, requires an additional setup of resampling to complete the process. There are different methods for transformation from one coordinate to another coordinate. Every method is distinguished by the geometric properties it can preserve and by the changes it allows. The effect of transformation varies from changes of the position and direction to a uniform change of scale to change in shape and size. The different transformation methods allow different properties like equa-area in transformation. In this transformation, it preserves the shape and size and allows rotation of the rectangle. Similarity transformation. In this transformation, preserves shape but not the size and allows rotation of the rectangle. Affine transformation. In this transformation, preserves the parallelism of lines and allows angular distortion of the rectangle. Projective transformation. Projective transformation. This transformation allows both angular end length distortion, thus allowing the rectangle to be transformed into any irregular quadrilateral. In majority cases, affine transformation method are used for map-to-map or image-to-map transformation, and the projective transformation are used for aerial photographs with relief displacement. Also available in GIS packages are general polynomial transformation that use surface generated from second or higher order polynomial equation to transform satellite images with higher degree of distortion and topographic relief displacement. The process of general polynomial transformation is commonly called wrapping. Control points. Control points plays key role in determining the accuracy of a affine transformation. The selection of control points, however, differs between map-to-map transformation and image-to-map transformation. The selection of control points for a map-to-map transformation is relatively straightforward. The basic needs are the points with known real-world coordinates. If it is not available, then points with known latitude and longitude values are projected into real-world coordinates. A USGS 1:24,000 scale quadrangle map has 16 points with known longitude and latitudinal values, 12 points along the border and 4 additional points with the quadrangle. These 16 points are also called ticks. An affine transformation requires a minimum of 3 control points to establish its 6th coefficient. But often 4 or more control points are used to reduce problems with measurement errors and allows for a least square solution. After the control points are selected, they are digitized along with map features onto the digitized map. Control points for an image to map transformation are usually called the ground control points. Ground control points are points where both image coordinates and real world coordinates can be identified. The ground control points are selected directly from a satellite image. Therefore, the selection is not as straightforward as selecting the ticks for the digitized map. Ideally, the ground control points are the features that show up clearly as a single distinct pixel. For example, include road intersection, rock outcrop, a small pond or distinctive feature along shorelines. Georeferencing a thematic map scene may require an initial set of 20 or more ground control points. Some of these points are eventually removed in the transformation process because they contribute to a large root mean square error. Caution: when evaluating transformation, selects the best transformation to apply is a subjective process guided by multiple goals. To develop an accurate transformation based on a large set of well distributed control points, isolated control points that substantially improve our coverage may also contribute substantially to our transformation errors. There are no clear rules on the number of points versus distribution of points trade-off, but it is typically best to strive for the widest distribution of points. At least 2 control points in each quadrant of the working area with a target of 20% in each quadrant. This is often not possible. This later reason is less common with the development of GNSS. The transformation equation should be developed with some observations in mind. First, bad control points happen, but we should thoroughly justify the removal of any control point. Every attempt should be made to identify the source of the error, either in the collection or in the processing of field. Second, a lower root mean square error does not mean a better transformation. The root mean square error is useful tool when comparing among transformations that have same model form. For example, when comparing one affine to another affine. The root mean square error is not useful when comparing among different model forms. For example, when comparing an affine to a second order polynomial. The root mean square error is typically lower for the second and other higher order polynomials than an affine transformation, but it does not mean the higher order polynomial provides a more accurate transformation. The higher order polynomial will introduce more error than an affine transformation on most orthographic maps. The first order transformation, the root mean square error is 6.7 meters maps, and an affine transformation is preferred. Control point sources. Surveying. The traditional ground surveys based on optical surveys measurement are a common, although decreasingly used method for determining control point location. Modern surveys uses complex instruments such as transits and theodolites to precisely measure the relative location of points. If the survey starts from a known point, then the coordinate location of any survey station may be determined via simple trigonometry functions. Federal, state, county and local governments all maintain a set of accurately surveyed location, and these points may be used as control points or as starting points for additional surveys. Many of these known points have been established using traditional surveying techniques. Indeed, the development of this control network infrastructure is one of the first and most important responsibilities of government. These survey points form the basis for distance, location and area measurements used to define property, political and municipal boundaries. Control points must have 2 characteristics to be useful. First, the point must be visible on the map, the data layer or the image that we wish to register. Second, we must have precise ground coordinates on our target map projection. The first requirement, visibility on the source map or photograph, is often not met for survey defined control. Therefore, we must often obtain additional control points. One option for obtaining the control points is to perform additional surveys that measure the coordinates of features that are visible on the source materials. The precise surveys are used to establish the coordinate location of a well distributed sufficient set of points throughout the area covered by the source map. While sometimes expensive, new surveys are the chosen method when the highest accuracy are required. Costs were prohibitive with traditional optical surveying methods. However, GNS positioning technologies allow more frequent custom collection of control points. Control points from existing map and digital data. Registered digital image data are common sources of ground control points, particularly when natural resources or municipal database are to be developed for managing large areas. Digital images often provide a richly detailed depiction of surface features. Digital images often provide a richly detailed depiction of surface features. Existing maps are another common source of controlling points. The point location are plotted and coordinates often point on maps. For example, the corner location coordinates are printed on USGS quadrangle maps. Road intersection and other well-defined locations are often represented on maps. If enough recognizable features can be identified, then control points may be obtained from the map. Control points derived in this manner typically come only from cartometric maps. These maps produced with the intent of giving an accurate map projected representation of features on the Earth's surface. The affine transformation uses the coefficients derived from a set of control points to transform a digitized map or a satellite image. The location of a control point on a digitized map or an image is an estimated location and can deviate from its actual location. A common measure of the goodness of the control point is the root mean square error, which measures the deviation between the actual and the estimated location. The root mean square error should be within a tolerance value. The data producer defines the tolerance value, which can vary by the accuracy and the map scale or by the ground resolution of the input data. A root mean square error of less than 6 meters is probably acceptable if the input map is a 1:24,000 scale USGS quadrangle map. If the root mean square error based on control point is within the acceptable range, then the assumption is that this same level of accuracy can also apply to its entire map or image, but this assumption may not be true under certain circumstances. For satellite images, this means removing the control points that contribute most of the root mean square error and replacing them with new ground control points. Geometric transformation is there for an alternative purpose of selecting control points, estimating the transformation coefficient and computing the root mean square error. Interpretation of root mean square error on digitized map. However, when the root mean square error is not under the acceptable range, if the gross errors are made in digitizing the control points or in putting the longitude and latitude readings of the control points. Longitude and latitude readings printed on a paper maps are sometimes erroneous. This would lead to acceptable root mean square error but significant location errors for digitized map features. Although we intend to take for granted the accuracy of published maps, Heron IAS longitude and latitude readings are quite common, especially with inset maps, that is, maps that are smaller than the regular size, and oversized maps, that is, maps that are larger than the regular size. We typically use the 4 corner points of the source map as control points. This practice makes sense because the exact reading of the longitude and latitude are usually shown at these points. Moreover, using the corner points as control points helps in the process of joining the map with its adjacent maps. But the practice of using for the corner control points does not preclude the use of more control points if additional points with known location are available. The affine transformation uses at least square solution when more than 3 control points are present. Therefore, The use of more control point means a better coverage of the entire map in transformation. In other situation, control points that are closer to the map feature of intersect should be used instead of the corner points. This ensures the location accuracy of these map features. Resampling of pixel value. When the new image is based on a projected coordinate system, the satellite image is geometrically transformed, but the new image has no pixel value. The pixel value must be filled through resampling. Resampling in this case means filling each pixel of the new image with value or its derived value from the original image. There are three common resampling methods used in geometric transformation: nearest neighbor, bilinear interpolation, cubic convolution. The nearest neighbor resampling method is used to fill each pixel of the new image with the nearest pixel value from the original image. For example, a figure having a pixel within a new image will take the value of pixel be in the original image because it is the closest neighbor. The nearest neighbor method is computationally efficient and has additional property of preserving the original pixel values, which is important for categorical data such as land cover, types, and desirable for some image processing such as edge deduction. Both bilinear interpolation and cubic convolution fill the new image with distance weighted averages of the pixel values from the original image. The bilinear interpolation method uses the average of 4 nearest pixel values from 3 linear interpolations, whereas the cubic convolution method uses the average of 16 nearest pixel values from 5 cubic polynomial interpolation. The cubic convolution tends to provide a smoother output than bilinear interpolation, but requires a longer processing time. There are other uses of resampling. Resampling is needed whenever there is a change of cell location or self size between the input raster and output raster. For example, projecting a raster from one coordinate system to another requires resampling to fill in the cell values of the outer raster. Resampling is used with pyramiding to build at different pyramid levels. Regardless of its application, resampling typically uses one of the 3 resampling methods to produce the output raster. GIS packages include ArcGIS have adopted pyramiding for displaying large raster data sets. Pyramiding builds different pyramid levels to represent reduced or lower resolution of a large raster. Because a lower resolution raster, that is a pyramid level of greater than 0, requires less memory space. It can display more quickly. Therefore, when viewing the entire raster, it is viewed at the highest pyramid level, and as we zoom in, we view more detailed data set, a final resolution, that is a pyramid level of closer to 0. Resampling is involved in building different pyramid levels. Summary. Geometric transformation plays a major role in converting data from one form into digitized form. This geometric transformation has to be accurate and should be devoid of errors. These geometric transformation helps in acquiring large amount of data as different data are digitized and added to the database.